last time we have seen how to implement an inverter with the MOS transistor with the resistive load. So we call this thing resistive load and MOS. You know, we said that implementing this consumes a lot of area in the chip. So therefore, we don't like that. But our concern is just digital operation, you know, 1 and 0. So if we give high, we would like to have a low output. And if we give low as the input, output should be high. So therefore, people started to investigate how to implement the load, you know, in a different way, in a smaller area. And one approach is to use maybe, you know, another transistor as the active element. So here is one version. We will see the advantages and disadvantages of this version also. You know, this type is called saturated only enhancement load NMOS approach. You know, why saturated only? Because this transistor is going to be in SAT always. Okay, why do we say it's in SAT? Remember the SAT condition? SAT means V drain to source is larger than V gate to source minus V threshold voltage, right? So here, this is drain, source, and gate. V gate to source is equal to V drain to source. Okay, so they are equal to each other. Therefore, 0, if we subtract this one, 0 is always larger than minus VTN. Okay, so always in SAT. So that is the case here. This is going to be enhancement load. I mean, this is a similar thing, but just we will be changing the bias voltage. Enhancement load. Calling enhancement load NMOS. And then this one is going to be depletion load NMOS approach. I will be talking about each of these, you know, step by step. So, you know, for this device to analyze that, we will look at in more detail now. So, if the input is, you know, less than this value, okay, so it could be 0 or VTN, okay. So, I mean, initially maybe Vin is equal to 0 or less than VTN. What happens? What happens? What is the state of, you know, output is supposed to be high, but what is Mn for this case? Mn is what?
Off.
Yes, Mn is off. So if Mn becomes off, what will happen? You know, I'll do something here just to make sure you feel comfortable about the result. If this is 5 volt, okay, this is your other transistor. So what is going to be this output? So in order to determine the output, let's say this is V out, I'm going to put here a load capacitor. And putting the load capacitor, that means, this is going to be charged, CL, okay, until the current becomes 0. Okay, CL will be charged up to the point where ICL becomes 0. So there is going to be a certain maximum. So we know that this is always in SAT. Okay. So if this is always in saturation, what is that current? So we know that IDS current, this is also equal to IDS of load. Okay. IDS load is going to be, since the transistor is in saturation, Kn load divided by 2, V gate to source load minus VTN load square. So if this is equal to 0, what is that, this voltage? Gate to source. From this,
VT, it is equal to VTN.
VTN of L, right?
Yes.
Okay, great. So what is V out? V gate to source, this is V gate to source of L. 5 minus okay, so let me, instead of say 5, VDD minus V T and L, as this is V gate to source of L. Is that clear?
Hocam sihir'in bulunmaması V'at'ı etkilemiyor mu?
No. Just this is to let you know that CL is charged through V out. Even if CL is not there, this is going to be the result. But that capacitor is going to be charged until the current becomes 0. So the maximum that V out can reach to is the point where the current through that load transistor to become 0. So just to make you feel comfortable. I don't know. I hope you are comfortable, but that's so the voltage here is up to VTN of VTN is going to be VDD minus VTN of L. Okay, so if VTN of L is 1 volt, VDD is 5 volt, then this is going to be 4 volt. But still, this is maybe high voltage, you know, this can be considered as a high voltage. So let's say this is the first case. That's not good, you know, having in the resistor, it was better. It was going up to 5 volt, but now it's maybe going up to 4 volts. And depending on the, maybe it's too early to confuse you with this, but if you think that these are in the same substrate, then threshold of this one, VTN of L is going to be equal to VTN of L at 0 volt plus, did you learn this before? Square root of V source to bulk minus 2 phi F minus square root of 2 phi F. Okay, so basically this was the gamma term, and then due to this, let's say this will be 1 plus, I don't know, depending on the gamma or so, all the voltages, it's going to be maybe even larger. Okay, let's say. So this is going to be about, let's say, 1.5 volts. So therefore, V output high is going to be equal to 5 minus 1.5 volts. So it's going to be maybe 3.5 volts. If the substrates are common. In common connection. Okay, so but if you think this way, maybe if you think that this is the case, substrate is here and this substrate is here, then this is VDD, this is connected like that, then VTN of L is going to be equal to 1 volt. Why? Because this substrate or source drain gate, this is the bulk. So here we source to bulk is going to be, let's say 4 volt, but if it's 4 volt, then the voltage will drop. So we can use iteration to find out the value. It settles and it's going to be something like 3.5 volts. Not good, but it's okay, you know, it's acceptable as a high voltage. If the substrate is connected, then this, I think I made a mistake here. This should be plus, yeah. So source to bulk is connected together. That's going to be 0. If that's 0, this whole thing will become, you know, inside 0. So it will be equal. Is that clear? So that's it initially. So what happens after that? You know, we will be always assuming now it's like this, right? It's convenient, more convenient. So let's draw it again here. Up to VTN. This is VDD minus VTN of L. So what happens if the input is larger than this? Slightly larger. Okay, now first, slightly larger. So for the slightly larger case, we know that ML still is in SAT. And that's always in SAT. What about MN? What about MN?
It is also
MN,
SAT, I think.
Maybe it's in SAT. Is it in SAT? Depends on V in voltage. Okay. Depends on V in. MN is on. So MN is on, and what is the case for SAT? We drain to source of N is larger than V gate to source of N minus VTN. Okay. So let's say this is slightly, maybe around 4 volts. Okay. So we know that this is 1 volt. So if the input, input is slightly larger than VTN, right? Slightly larger than. Larger than what? Larger than VTN. So therefore, this will be in SAT also. Okay. So both transistors are in SAT. You know, until, but if this is V in, and this is V out, okay? So when V in increases, V out will be decreasing. So at some point, MN will switch to linear mode, but MN will go to linear mode, but ML will be remaining in SAT because it cannot change due to electrical connection. Okay, so if both transistors are in SAT, okay, we know that I drain to source of L should be equal to what is I drain to source of L? Kn of L, divided by 2, V gate to source of L minus V threshold of N of L square. What about I drain to source of N? That's Kn, or Kn of 2, V gate to source of N minus V threshold of N square. Is that okay? So we know that electrical connection forces them to be equal to 0, to each other. So I ds of L should be equal to I ds of N circuit. Forces. So if you look at this, this is equal to this one. So if we look at the gate to source, what is gate to source of L? So what is gate to source of N? This is V in. What about this one? VDD minus V out. Okay. So we can have a V in, V out relationship. Okay. So, we don't have to really find the whole equation here, but if you look at this, and they're equal to each other, so maybe I can do this. Their 2's are canceled, and the we can take square root of both of the sides. In fact, when you do all the math, you will see that V out divided by V in is going to be proportional to minus, because of the slopes are actually going to be minus, something minus V out, it's going to be K N of L divided by K N. So basically, what will happen? This is going to be what's going to be happening. So the slope is going to be minus square root of K N of L divided by Kn. Okay. Is this correct? Did I make a mistake? Or it's the other way around? It is the other way around. You see? Nobody is warning me. K N divided by K N of L. Which one is correct? This will go.
Correct.
This will go to the denominator. Yeah. So the logic behind is that what is Kn? Remember? Anybody who remembers what is Kn? How do we define Kn?
C of W over L.
CO W divided by L. Maybe I'll put this. Okay. So so what about Kn of L? Again, mu n C oxide divided by WL of maybe L. Okay. So since the transistors are same, this should be same, this should be same, they are same. Therefore, WR ratio will determine that Kn value for each transistor. Okay. So if Kn is larger, okay, that means Mn is stronger. Okay, so this is interesting definition. Then the slope will be sharper. Okay, so if that value is larger, then the slope will be larger. Is that clear? So if we continue this graph, you will notice that, after a while, up to a certain point, this is going to be where maybe this is maybe second case. And then after this, the transistor, the third case, Mn will go into linear mode. So here, Mn sat, here, Mn in linear mode. It cannot provide too much current now. So the transition is not going to be that strong. So as the definition again, if the input is V output high, maybe I should change that in color. If the input is V output high, which is V output high, corresponding value here is going to be V output low. That's the definition. Is it okay? So that point is determined as Vx, as you see here. So maybe this value is Vx. So if your transistor is stronger, then this will be again up to maybe a certain point. Vx is going to be here. I don't know. This is too sharp, yeah. I don't like this as being too sharp. I messed up. And it will be going like this. What am I making? I'm making a mistake here. That Vx point, maybe it's not going to the same point. It's going to the same point. Same voltage of Vn. this, might not be at the same Vx. So let me just erase that part because I'm not sure. I don't want to make a mistake here. But just to let you know this much, oops. This will be going like this. Okay, I'm not going to complete that drawing because I'm not sure if the same Vx's are happening there. So in any case, going back to the drawing here, this is up to VTN. And then we see that it comes linearly up to this maybe Vx point. And here ML sat. ML is always sat, so I don't need to write that. ML is always in sat. So here is MN of MN sat. And then after this, MN linear. So after this, this will be reducing like this. Oops. Okay, like that. Okay. So this value here, it's going to be V output high. When the input is output high, the corresponding output is V output low. And this is VDD minus VTN of L. Okay. So we can call this one as V input low now, because that's the corner point. And the slope, when the slope becomes -1 here, maybe I should do this maybe more properly. This will be called V input high. So that's what happens. Okay. At after the point Vn is equal to Vx, then Mn becomes linear, or goes into linear mode. Okay, so if you want to find this value, you need to write the equation. And how can you find it here? What is V output low? We need to just solve the equations here. You know that IDS of L is equal to IDS of N. So IDS of L, since it's always in saturation, so Kn of L divided by 2, we gate the source. That means VDD minus Vout minus V threshold of N of L square. So this one is V gate to source of L, and is equal to K of N V gate to source of N, which is V in, V gate to source of N, minus V threshold of N square, sorry, not square, V drain to source of N, which is V out, minus V drain to source of N square divided by 2. Okay, so what should be the input voltage? What is this one? This is the input voltage, right? So that value, when this is equal to VDD minus VTN of L, then the only unknown is V out. So this is V out, this is V out, this is V out. Okay, so that value of V out is going to be then the output law. So there's only one unknown, so you just need to solve the equation here. Okay, you can find V out, which is also equal to V output law. Is that clear?
Hocam. Burada Vx değerinin de Vtn of n olduğunu söyleyebilir miyiz?
Vx değeri Vtn. I mean that, no, I mean Vx, what is Vx? Vx is the point where V drain to source is equal to V gate to source minus Vtn. Okay, so that's the point. So drain to source is V out and is equal to V in minus Vtn. Okay, so the difference between V out and V in is equal to minus Vtn is the point. Is that okay? That's the critical point. VDS becomes lower than V gate to source minus V threshold of N. That's the value of Vx.
Hocam çok özür dilerim ama az önce düştüm. Söylediklerinizi kaçırdım. Tekrar edebilir misiniz?
So if you want to find the Vx is the point where the transistor goes from SAT to linear, right? So that critical point is this point. Drain to source is equal to gate to source minus Vtn. So that value can be determined from here. I mean, that's the point where V out is equal to Vx minus Vtn. You know, this one, this value, you know that this is the slope. So from the slope, you can find that value, you know, for which value, where this becomes, you know, here. So from the previous slope, you know, the slope here, you know, slope. What was the slope? Minus Kn divided by Knl. So from this equation, you can find that value. I mean, here, you know this one, and you know this one. So from there, and then from this equation, maybe this is equation 2. This is going to be giving you 1 ratio. And from those 2 equations, and this is fixed, the output I is fixed. So you can find that value. Let's call this thing Vy. Okay, here we call this thing Vy, right? So, you know, we output high minus Vy. We output high minus Vy divided by Vx minus Vy is going to be equal to minus, is there going to be minus or plus? Is going to be plus Kn divided by Knl. So this is equation 1 and then equation 2, and then we can find that Vx and Vy values. Is that clear?
Evet hocam, teşekkür ederim.
Sure. So, I mean, I guess we already have found the output low and output high cases. So the definitions are given. Maybe we should draw this again. Like, this is not going to go this way, by the way. As you know, this will go like this, and then after that, it will be going like that. Okay, so this will not be the case for this one. So this is going to be Vx, this will be Vy, and then this point is going to be VDD minus Vtn of L, which will be V output high, and that V output high corresponding output is going to be output low. Okay, so you know, you need to solve it for that, as mentioned here. This is the input high, and the input low, I mean, oh, sorry. This is the input low. Shall I erase it like this? No. Can erase it like this. Okay, I cleaned it up. And this is where the slope is -1, and this point will be the input high. And we can also calculate it in there, and you know, we input high is the point point where the slope is equal to -1. Okay. So for this case, this happens where? Where does this happen? For the number 1, 2, and 3. So for case 3, Mn in linear mode, Ml, of course, in SAT. This is always. Okay. And, you know, we can again do partial derivatives and then, you know, find that out. If you take derivative of I drain to source of n with respect to, you know, right now, maybe we need to do partial derivative here. V in and V out. And then we need to take ideas of L with respect to, you know, that depends only on V out. So we don't need to do partial derivative actually. This is going to be just derivative like this. Then from here, we can find dV out divided by dV in to be equal to -1. So that's going to be the point for V input I. Again, you know, I'll be distributing some things for you. So either we need to give a break and continue or just continue. I mean, I guess we are going ahead of the slides because these are just mentioned here. Load line approach is also possible to solve the data. So what shall we do today? Shall we continue or give a break and continue? If we are going to not go full hour, then I like to maybe mention about load line approach and then stop. What do you say? I don't know. Or I can just give a break now and then continue a little bit more, but not the full hour. Okay, now the load line, we can find the transfer function using load line analysis again. Now the load line analysis is, let me draw it first here. So this is, as you know, drain, source, and gate. Drain, source, and gate. So for ML transistor, again, we'll be assuming that these are connected like this. So that's it. So for ML, what is the voltage current equation? So if we consider V drain to source of L, I drain to source of L. What is the curve here? V drain to source of L is equal to V DD minus V out. I drain to source of N. Now, let me do this. That transistor I drain to the source of L is equal to Kn of L divided by 2 V gate to source of L minus Vtn of L square. We don't need to go to that, this graphic. We know that transistor always is going to be following this this thing. What is this? Gate to source of L. Gate to source of L is equal to VDD minus V out. Okay, so we really don't need this. And this one is equal to I drain to the source of N. So I drain to source of N is equal to I drain to source of L. V drain to source of N is equal to VDD minus V out, or V out, yeah. Sorry, that's a mistake. If I put this here as V drain to the source of N, V out is V drain to source of N. So inside of this, I can rearrange, and it's going to VDD minus V threshold of N of L minus V drain to source of N square. So if this is 1 volt, for example, so if I draw this, Kn of L of 2, if I draw this is like you learned this, right? In your high school. This is it, right? Parabola.
Yes.
So, of course, we will not be using this side because that goes beyond the voltages. Because the maximum of VDS of N is equal to what? VDD minus V threshold of NL. So our load line is going to be this. So can you tell me what is this point? Where both transistors are in SAT, the end of that. And then here, Mn goes to linear. So what is that V out value? We define that. What is that value?
Vx.
No, but at the output, what did we say?
Vx minus Vtn.
No.
Vy.
Yeah, that's Vy. Okay. So that's Vy. So the solutions. Okay, now we can look at the solutions. Here is one solution, and that corresponds to this line. This line. What is that line? V in lower than Vtn. So that's point A. So this line is the whole group is A up to Vtn. Okay. So the second point is this one, cross-section point B. Of course, there are many lines here, but we are ignoring that. We're just looking at the values here. So B is somewhere around here. That because this is output, right? So in terms of output, maybe it's somewhere around here. So that's B. And we know that both of them are in SAT mode, therefore it should be linear, because this is Mn SAT and MNL or ML also SAT. So therefore it will go linear, and somewhere around here we have continue. If we continue, this will be coming to Vy, and then after Vy it goes into linear mode. So maybe this is going to be C, this will be D, and E, maybe. I don't know, depending on the voltages here, like how we define it. But, there's going to be maybe B, and then, I don't know, C, and E, or D and E. Okay, so this is how we obtain the result from graphics also.
Hocam,
Mm-hmm.
at which point it goes to linear?
I mean, you can find that out as we discussed here. From this, you can find that value. Okay.
Okay.
We discussed that before. Yeah. I mean, but in terms of here, this is the point. Because this is when it starts. And then this is, of course, ML sat always. So and this corresponding value, we call it Vx. We output high. So we output high minus Vy divided by Vx minus Vtn is equal to what? Is equal to square root of Kn divided by Kn. So this is one equation, and then there was another equation. You can find that out. What was our equation? Vy is equal to Vx minus Vtn. Where does this come from? What is Vx? Vds is equal to V gate to source minus V threshold of n. Did we make a mistake there? No, or the NMOS. Mn. This is the case, right? Because this is V out is equal to V in minus Vtn. This is the point where Mn becomes linear. So that's the critical point. So this is the second equation. Okay, two equations, two unknowns, and Vx and Vy can be found and determined. Is that clear?
Yes, hocam.
Okay, so you know, this is then a way to do this, but we noticed that here we output high is equal to VDD minus V threshold of NL. Okay, so that's not good. You know, if we increase that gate voltage instead of VDD, V bias, which is VDD plus VTNL, then V out becomes V output high becomes VDD. Okay. Gate to source drain to source. This should be the case, yeah. Is this correct? I'm not sure. What is the status of the transistor here? The transistor, what about V drain to source of L corresponding to V gate to source of L minus V threshold of L? VDD drain to source of L is 0 for this case. Gate to source of L is VDD minus V threshold of N of L. So is that consistent? This is going to be, this becomes linear mode though, right? Drain to source equal to gate to source. Drain to source. Uh-oh, I'm confused. Yeah, sorry, this is going to be gate to source. Gate to source is equal to VDD plus this one, V gate, and then minus the source, VDD. Yeah, so it will be consistent. Threshold voltage, that's going to be equal to each other. So it's going to be 0 is equal to 0. So it's the transition point from linear to SAT. So the equations will be consistent. So when this is off, current is 0. Drain source of N is equal to 0. So again, the output high is going to be VDD. So this will be okay. You know, so SAT, for this case, load is going to be in SAT again. So, you know, output high can be good for output high case, but a second supply voltage becomes necessary. Okay, not preferred. But you know, it is a possibility. So people came up with another idea. This became more popular. You know, people start to say, you know, why not just do this in the fabrication? I mean, you know that this will be the substrate, and this will be N plus and N plus for one transistor, and this will be N plus and N plus for the second transistor. Let's say this is substrate P plus. So instead of, you know, drawing this separately, the bias, it could be same bias. And then just do this and connect to ground and connect this to ground. So this is the MN, VN. And then this one is connected to here electrically. And this is the second transistor. Okay. And for the second transistor, connect this one to VDD. And this one, connect electrically to V out. And this is going to be our V out. Okay. So a simple addition here of N minus, lightly doping that layer, gives us this depletion load. Okay, so this becomes depletion transistor. And just by doing that simple addition, output high becomes VDD when this is off. Why? Just by looking at this, I mean, we have a resistance between this point and this point. That N minus line, you know, gives you resistance. So here the current is zero. So if the current is zero and there is a resistance there, the voltage drop across that is going to be 0 volt, and then V out becomes VDD. Does it make sense? So I guess we should continue on this here. We can find that out, that value as VDD, you know, from equations also. And we can also draw, let's say, the graphical analysis and then find that out. But, you know, really the NMOS technology was used. So instead of just a simple, you know, one type of transistor, this is enhancement transistor, this is enhancement. Just by doing, you know, one simple addition of doping, people obtain this device. So this is MN, this is ML. And then, you know, increase that output voltage to VDD. Okay, so the output low is not equal to 0 again, but this one is good. So I'll stop here. Next time, we'll start from here and then obtain the graphics here. But, you know, I can just maybe quickly show here that up to VTN, output is going to VDD, which is going to be output high here. And we can find that, you know, value from equations also. I mean, I'm tempted to continue, but there are so many things. Once we start, we should continue. So maybe we will be doing that next time. Is that okay? Or if you have the energy, I can continue.
I think okay hocam.
So you mean you have the energy to continue
No, I mean,
or
I
stop here?
finish, and maybe next lesson we will have more people so they can enjoy the class also.
Oh, okay. So that's a good excuse. Okay, let me stop then. Okay. Tamam. O zaman